Welcome to Spacesuit Gases 101, and why we run 3.5 to 4.5 or so psi of pure oxygen, and what the meaning behind all that math is. So, first things first. In the atmosphere we live in right now, at 14.7 psi A, or absolute, relative to zero, and also known as 1 atmosphere, we have in our atmosphere right now 78.5% nitrogen and 21% oxygen. The 0.5 missing out of that equation is for trace gases that do not matter to us right now and therefore will be ignored going forward in this discussion. Now, as you probably have noticed here, the bottom half of this magical tube is green. That's the visual representation to show how much oxygen is in the actual air. There is pure O2 in the air and pure nitrogen, making a blend called air. So if you were to separate the parts out, so it's not just one muddy color full of both gases, and you made them pure, that's the visual representation of the ratio you're going to see involved. Now, in a spacesuit, we run at lower pressure, okay? So the amount of oxygen you see in the bottom half of the left-hand cylinder is expanded to a lower pressure to be the amount in the middle cylinder. And that distinction is that it's the same amount of molecules of oxygen. At the end of the day, the amount of oxygen, molar-wise, is the same on the left hand and the middle hand. Simply, the partial pressure, or the partial amount, if you will, is obviously have to do with nitrogen now. You know, almost 80% of the gas in air is nitrogen. If that's removed, what's left is oxygen at a lower pressure. Makes sense? So that mixture of pure O2 would be equivalent of, when expanded out, of 3 psi absolute, also known as 0.21 atmospheres. Actually 3.01. I rounded it a tiny bit here, and it's close enough. So that's the amount of pure oxygen in the suit. That's not the nitrogen. Makes sense? So if you remove the nitrogen, that's what's left. And of course, it's got to fill, because there's no nitrogen to help bulk it up, it expands to that void, i.e. lower pressure, about that 3.0 psi or so. Now, the thing is this. Your body will kind of live with this pressure, almost up to an extent. It's not good. Your lungs will not transfer gases very well at 3 psi absolute. So we have found out that it's really the best in spacesuits to run around 3.6, 3.7 on the Apollo suits, and then up to around 4.1, 4.2 psi on more modern suits. That's because of the fact that we have to accommodate, should I say. We have to accommodate the fact we got to go through pre-breathing to become pure O2 in our bodies, flush out nitrogen so you don't get the bends, we leave the airlock. It's a lot of procedural-based things, and it's easier to go from the left to the right than the left to the middle. Put it simply, because in the ISS is the left hand, right here, 14.7 psi A, which of that is air we have on Earth. The reason why is this. Flammability is a very high accelerant. It will accelerate existing flames and fires rapidly. And so by having nitrogen be in there, functionally have created the same fire hazard, like explosion-wise, as on Earth. So that makes things a lot safer, like laptops, for example. We can have laptop batteries in orbit. I mean, I wouldn't want to put my battery in pure oxygen, but it would be just fine in things like standard air. Now, it does mean that the hull, that at 14.7 psi or 1 atmosphere, you do have a lot more stress on the physical hull of the ISS, or a spacesuit for that matter, right? So there is a balance here. The reason why we run pure O2 in a spacesuit is many things, and they're equally important, right? One of them is nitrogen isn't doing anything useful. It's just taking up space in the cylinder, either liquefied for long-term use or gas in a compressed gas cylinder for the back of the EVA backpack, and that gas is just there along for the ride. It's a waste of space, literally. Number two, complexity. You got to have now, or you can have 2 gas cylinders, one of both, and to mix them live, more valving. That's not very fun. Look at rebreathers for divers. You have to deal with diluent gases and pure O2. That's a complexity in itself. And then also pressure. The fact that you can run 3.5 psi and be alive means that your suit can be a lot weaker, about a quarter as strong for a given safety factor as a full, like I said, full pressure suit would be. So no one runs 14.7 psi spacesuits. That's just silly. Because, they're mechanically way more rugged and robust and hard to make and heavy and cumbersome, and really it's a good balance. So Puro 2 is a solution, and because it's a very controlled environment, it's pretty safe. Sure, there's still a fire hazard, but you're not like you're running open flame candle tests inside your spacesuit, but you would be on the ISS. And the ISS had to have micro welding, lasers, heat sources, matches, flames. They got all kinds of flammable stuff up in the ISS. And therefore, that's why shuttle and ISS, for the sciencey stuff, went to Earth's atmosphere because it's safer, at the expense of a thicker hull than necessary than if you're on Puro 2. And there you go. Thanks for my talk on these gases. It's fascinating, and we'll have more of a premiere on how the oxygen system works on a spacesuit coming up pretty soon.